Hey, good afternoon, folks. Can you guys hear me and see the image? Good, good. Thank you. All right, let's get started. I looked at your grades. The grades are doing, you guys are doing fine, but I have to let you know that the average on the first midterm was 92%. That means everyone, the average was A. But it's not going to be like that for the second midterm. You got to study hard. So that built up your confidence, which is good. Now, questions are going to be a little bit more challenging because of the topics that I have covered. And it's going to be similar types of questions, but it's going to be more challenging, so to speak. It's going to be from the book, and it's going to be the same method, same thing's going to happen. And also, after the class, I'm going to put the distribution of grades into Canvas, meaning that I'm going to drop the lowest score of each assignment. That means I'm going to drop lowest score of web work, 1, and 1 Excel, and 1 tutorials, is the discussion section. So I'm going to include those. Those are going to improve your grades, possibly. And also, I'm going to put the percentage of each part of the assignment. So like midterms are 18%. I don't remember exactly, but whatever the percentage is, I'm going to put them in Canvas, so it's going to be more realistic what your grade is. So, all right, last time we started on chapter 16, and basically from here on, it's inference. And inference has two topics that we are going to deal with that. One is confidence intervals, and the other one is tests of significance. So chapter 16, it's dealing with confidence intervals. And we went through this last time a bit. We talked about it. So basically, what we have here, mu is unknown for confidence interval. So, and sigma is known. And we said that there's a formula for confidence interval. Confidence interval is equal to, and that formula is x minus d, comma, x plus d. And x is, maybe you can write x bar if you want it, basically is the estimate for the average of the population, mu. Basically, we are looking at that one, estimate of population, what the average is. And d is margin of errors. You're going to see that there's a formula for that. And basically, confidence interval is going to happen between these two. When we say, like, the confidence interval for a parameter, it's 95%. What it means, if you do the testing, calculate that X bar and try to average out and figure out what the population mean is, you're going to see 95% of the time it's going to lie between these two values. Another way of saying it, if you do the testing 100 times, 95 out of 100, the mean is going to happen, the mean of the population is going to happen between these two values. That's all we are doing. We call this confidence interval, and it could be 95% confidence interval, 90, 80%, 99%. It depends on how we are dealing with things. Here, what we have is there is a 95% chance that a parameter we are trying to measure is between this and that. Again, if we are dealing with the average, that would be x bar. And let's do one example here. Example, I can put actually this example on Canvas, the data. Maybe you should see the data, but it says, consider the data from 2014 NFL team stats, document on Canvas. I'm going to put it on Canvas, and consider the points per game value. So I have copy of this. This is what we have. You can see basically we have different games here, name of teams like Green Bay, Denver, Philadelphia, and so forth and so on. These are per yards, but our interest lies on the last column, points per game. That's the average, points per game. So what I'm going to do, I'm going to use this table. I will put this table on Canvas, then you have it. What I'm going to do, I'm going to use this table and pick 4 samples from this table and calculate the, the confidence interval and so forth and so on. So that is going to be the table we are going to use. Okay. So population standard deviation is given. Um, standard deviation for points per game is four point. Okay, it's 4.37. That is sigma. Sigma is given. Okay, so now I randomly pick 4 samples. So you're going to see that you can do the same thing at home. You're going to see that similar thing that you'll come up with the similar examples. So my samples are, the number are 28. Randomly, I pick this, 21, 2, and 15. And each time when I pick this, my sample size was 4, basically. What happened here, so I pick the numbers here, and first randomly, you can use that table B, and or you can use Excel. So there are 32 teams. Put the numbers between 0 and 32, 1 and 32, and multiply it by 100, so you can get from 1 to 32. So basically, I came up with number 28. 28 is New York Jets. Then it was 21. 21 was St. Louis. And then it was, the third one was 2. And 2 is Denver. And the last one was 15, it was Cincinnati. So anyhow, we have New York Jets. 21 is St. Louis Rams, I think. Now it's with Los Angeles. 2 is Denver Bronco. 15 is Cincinnati Bengals. Bengals. Anyhow, so those are, just randomly pick 4. You can pick any sample. Here I pick 4, the size to be 4. So I'm working on 4. Okay. Okay, never mind. 14, thank you. Okay. So you can pick any numbers. This is what I did. All right. So the average, the points are here. So what I did, so let me just say what I got here. This is the value I got here, the team. You can see for team 1, this was New York Jets. Then team 2 was 21. Team 2 was St. Louis Rams. Team 2, 21. 2 was Bronco, Denver Bronco, and the last one was Cincinnati Bengals. So these are the average points per game. It's given on the last column. So I picked, again, I'm just going to say that. I picked these numbers randomly, use table B or use Excel. So these are the teams. I put team 1, 2, 3, 4, and looked at the points per game at the end, the last column. And these are the averages per game. Basically, that's what they got. Now, my sample mean would be average of these 4 because n is 4. So that would be 22.725. Okay? The population average, we're going to see that it's 22.6. I'm not going to talk, assuming that we don't know, but we are going to calculate that. We're going to see that this is going to fall within the confidence interval. What do we have? And the standard deviation of the population is given to us 4.37. Okay, we got it from the table, all these information. So I'm going to rewrite it here. So X bar, I'm going to write it here. X bar is equal to 22.75, 22.2, 22 point, sorry, 22.725. And then what we have mu is 22.6. And sigma, we said it was 4.37. Those are given, okay? We calculated this X bar. All we did, we added these 4 divided by 4. All right, now let's move on to see what the questions are. The next one. In what interval can we say with approximately 68% accuracy that the mu is contained within? Okay, so basically we want to know what is the interval of 68%. When you have a confidence interval is 68%, confidence level, we call this confidence level, EL is 68%. So we want to know what happens to the mu, how far, what is the range for mu. Remember, mu is given to us. Suppose even if you don't know what this mu is, based on what you get from here, you're going to say 68% of the time that when you calculate, when you get the average is going to happen, it's going to be close to the mu. 68% of the time, it's going to be within that interval. Let me just go through the calculation. You're going to see what's going on. We're going to do so many of this because you have to know how to do this. It's going to be in the midterm too. So 68%, that's confidence level, and we have these values. So if I want to write confidence interval, so that would be equal to X bar minus D, comma, X bar plus D. Oops. We have X bar is 22.725. D. D is called margin of errors. And the way we calculate D, we're going to see that there is a, let me just do it this way now. So it says 68%. 68% is within 1 sigma, right? So this D is going to represent basically 1 sigma divided by square root of n. N is the size of sample that we have, 4. So sigma is 4.37 divided by square root of n. The size of sample is 4. So if you simplify this, this becomes 2.185. Would be 2. Square root of 4 is 2. And that divided by that, you get this number. By the way, thank you to the person who suggested that I should use pencil. I think it's much better. You guys are right. Okay, so now we are going to write CI, confidence interval. So X bar is, we calculated is 22.725, 22.725. So the lower point, you have to subtract this, minus D, 2.185. The upper part is going to be this plus that. So 22.725 plus 2.185. Okay. Now, if we calculate this, CI, confidence interval, if you subtract this, it's going to be 20.54, comma, and if you add those numbers, it's going to be 24.185. Okay. You see that this is one time I did the measurement, and I see that mu is 22.6. It lies between these two numbers, right? If I continue doing this 100 times, 68 times out of the 100 times, you're going to see that the mu is going to fall between these two numbers. So whatever the numbers are going to be, always 68% of the time, that mu is going to fall between those two numbers when you calculate. Another way of saying it, if you increase confidence interval, you go to 95%. So that means in 95%, if you do the measurements with this sample that the way we did here, 100 times, 95 times, population mean is going to fall within that confidence interval. Then the second number be 24.91. Did I make a mistake? Okay, probably. See, I have a razor to clean it. Erase it. It's much cleaner now. 24.91. Okay. Are we okay with the concept? Because I want to make sure that you understand the concept. The concept is based on confidence level. We want to know where the value of population lies. I mean, it's going to lie between these two values, but I want to make sure that with the 95% confidence interval, 68, what percentage of confidence interval I want to do this? Where did the 22.6 come from? Is that the mean of all 32? Yes, that's the population. We already got it, right? In general, you don't have this. This is unknown. You're calculating to see that whether your mu, when you get this confidence interval, then you're going to say within this confidence interval of 68%, my population averages between these two numbers. That's what you say. Okay. Like when you're dealing with 2 million, you have no idea what the population mean is. But if someone says that, hey, with 95% confidence interval, can you tell me that what the population, and give me a sample, the size of the sample, I can do that and I can say that, yeah, it will happen between these two. Although I don't know the exact number, but I know that 95% of the time, if you measure it, it's going to be in between those two numbers. This is good. Okay. So maybe I should draw a curve here that you can see basically if this is the curve we have. So we already had this X bar here and it says 68%. 68% would be 1 sigma. So that would be, we say our mu is going to happen. This is going to be X bar plus sigma, X bar minus sigma. This is what we have here. But we know that this mu is not exactly the same as this. But if you, let's put numbers here. What do we have here? X bar plus sigma, that would be X bar plus sigma, that would be 26, almost 27 something. And if you subtract that, this would be 18 something, right? This is the 68% that you're dealing. But now we are looking at the mu. Mu is going to go back and forth within the 68% of time. It's going to be between these two numbers. That's all it says, those two numbers. Will margin of error always be sigma divided by square root of? It's not sigma. You're going to have a critical value we call z star. And z star represents within 1 sigma, 2 sigmas, 1.5 sigma, 1.3 sigmas, whatever the whole thing is. So based on that, and that goes back to the confidence level. We'll get there. That's a good question. Yes, we'll get there. Let me give you some pictorial example. This is from your textbook. This is what we have here. This is the population. Within the population, you have sigma 7.5, and then we pick the SRS, random sample, and the size is 654. So you calculate this. You can see that you calculate this and you find the X bar. And when you find X bar plus or minus 6, you added this. X bar for this one is 27, and X bar for that one is 26.2. For every sample you pick, you have a different X bar, but the confidence interval is going to be the same for the margin of error is going to be the same for all of them. Because if you pick like a 95%, you're picking 95% for every sample you pick. Anyhow, this is the one I'm talking about. You sampled once, you sampled, this is say, well, for 95%. Here it says 95%. So that means if I do this 100 of these, definitely out of 100, 95 of these samples that I have here, I know that the mu, the average, the population mean is going to be between those two numbers that I have. Another way of saying it, here what we have, here the you have, these are, this is calculate, this is 25 times. So 25 times, 1 out of 20, which is 25 times, that means 4 times like a, so you can see that these are the mean of each sample. You pick that, we are saying that it matches with the mean of the population, right? This is the calculation for, like the first one is this one, calculate X bar. The second one is this one, and so forth and so on. If you have 100 of these, 95 times, when you calculate this mu is going to be within the range of sampling. Only 5 times it's going to be outside the sample, outside the measurement with the sample. What does CL, the 65% do then? 65%, it's just a confidence level. That means you have a lower confidence level. So that means you're going to have more errors. So that means if you go with the 65%, that means if I do the measurements, here I have these SRSs, right? If I do 100 of these, only within the 65 of them I can find the right mu. The rest is going to be outside that. So that means, so you're going to have more reds. You're going to have 35 of these reds in 100 million. That means you have less confidence to have accurate answer, finding the right mu. Does it make sense? Emily? Okay. It's the idea that you've seen it on TV. We do this with the 95 confidence interval. We plus and minus margin of error 4% on the polling, and all the things that you do. When you say 95% or 99%, you're really confident. That means whoever does the measurement, 99%, 99 out of 100, you know that your average is within that two numbers. Whatever you, whoever the sample does the sampling, you know that definitely 99%, 99 of those samples that you do the measurement, your mu is going to happen within that interval. Here is another one. Here you can see this is the same thing. We are going to talk about this. Then you're going to see Z star here. So this is basically that probability. That's why when you say 95%, you're looking at within this 95%. So within the 95%, you want to know what the interval. This is a confidence interval. You're giving the confidence interval, and you want to see what happens to the mu, basically. This is for standard, normal standard calculation, because mu is X bar, mu is equal to 0. We'll get there too. Just a second. Let me just go through some examples you can see. Here, let's look at this one. Part C, it says, we are calculating this. Now it says, in what interval can we say the approximately 95% accuracy that the mu is contained within? So we want to know what is the interval that for 95%, if I do my measurements, I know that 95 out of 100 times, the mu is going to happen within that measurements. Whatever the measurements I'm doing, I'm confident 95% of the time it's going to happen there. Okay, let's just do this again. So 95%, if you do that, 95% represents, if you recall that this is 68% was 1 sigma, 95% is a 2 sigma. Remember that? 2 sigma. Okay. And here we have the exact value. We know that it's 2 sigma. But when you look at the table, we are going to use table C. In table C, you'll have more accuracy. That means it's not exactly 2, it's 1.96. And sometimes you have to use table C, sometimes you have to use table A, come up with the exact value. Like if the accuracy is you're dealing with, I don't know, 97%. If you don't have 97%, then you have to calculate that. And I'll show you how to calculate those values. Okay, let's do this. Again, we have confidence interval. We're calculating this. We have confidence level is 95%. 95% corresponds to 2 sigmas, right? Plus or minus 2 sigmas. So we are going to write x bar minus d, comma, x bar plus d. Now your d is different. For 95% confidence interval, you have to go to the 2 sigmas, because that's going to be your confidence interval you're adding. So therefore, your d is going to be a 2 times sigma divided by square root of n. Later on, you're going to see that this 2, we are going to replace 1 or 2 or whatever the numbers are you're looking at, it 1.5, we're going to replace it with the z star, and we call that critical value. We are going to have very general formula, we are going to use that. But here I'm going through 1 sigma, 2 sigma. 1 sigma represented 68%, 2 sigmas representing 95% confidence interval. So we have to just calculate this, and d would be 2 times 2 times what was sigma? Sigma was 4.37. 4.37 square root of 4. That is 2. 2 and 2 cancel, so 4.37. That would be d. Now, if you want to write confidence interval, that would be, we had x bar. What was the x bar? In the previous calculation, x bar was 22.725. So that would be 22.725 minus 4.37. That's a lower bound. The upper bound would be 22.725 plus 437. So if we do the addition and subtraction, so you have 18.355, 27.095. So basically, you can see that the confidence interval got wider, because now you're looking at for 95% of confidence interval. So you want to make sure that definitely it's going to happen. What is the question? When you found D, how did you know to use 4 in the denominator? Our sample size is n is 4. Yes, we use that one, 4. N was 4. Maybe I should have written here 4. Because remember, we picked 4 teams: St. Louis, New York Jets, and what was it, Bronco, Denver, and Bengals, Cincinnati. There were 4 teams. So that's the size of the sample. Okay, and this stands for 95%. This area is 95%. Okay, it says use the fact that population mean value of the points per game is in fact 22.6. Describe the accuracy of computation. You can easily see that with the 95% confidence interval, That's the mean. Mean lies between those two numbers. Definitely, you can see that. And in the previous calculation with 68%, for that, for the sample we picked, again, 22.6 lies between these two, right? So that proves what we are doing is correct. So again, if you do this one 100 times, 5 times it's not going to be between those two numbers. Only 95 out of 5 it's going to be between those two numbers. So basically we say each interval has population mean, right? So this is what we have. In general, a confidence interval for unknown parameter, always unknown parameter. It's not always mean. Sometimes you're going to see that we have other parameters too. We'll talk about those later. But in this case, we're looking at the mean. Is the form of you have the estimate. This is we are estimating the mean of the population in this case. This is the estimate. And you have plus and minus margin of errors. Margin of error is the minus part goes to the lower bound. We said that here. That's the minus. And plus goes to the upper bound. This is the formula we have. Minus, plus. This is the estimate. This is the margin of error. And this is the margin of error. Okay. So what the estimate is statistic. Yeah, this is statistic associated with the unknown parameter. So this is always something that it's unknown that you're using the statistic, that means samples, to extrapolate information about the population, which we call a parameter, and which is unknown. There are other parameters too, like you might deal with sigma, you might deal with other values. Okay, and the margin of error is the numerical value according to possible variation only from random sampling. Because of the random sampling, you do the random sampling, you have margin of error, and that's it's fixed if you have for whatever the samples are. The only thing changes if you change your samples. Like we pick 4 teams. Now, if we pick different 4 teams, my average is going to be different, but my margin of error is going to be the same. And then I'm going to add and subtract that, and I'm going to look at the mean, and I'm going to say, okay, 95% of that, if I do this calculation, it's going to have the mean is going to be between those two numbers. Not other kind, poor sampling, not other kind. Okay, so basically this is for mu. X bar, it's basically the estimate. And we are going to deal with Z star, as I mentioned that. Let me just write a formula. In the next page, you'll see this. It's sigma over square root of n. This is the critical value. Remember, so you get this value from confidence level. If confidence level was 68%, this value was 1 sigma. If the confidence level was 95%, this value became 2, right? If it's 3, if it's 2 point something, we'll get there. So you're going to see that it changes. So we need to have a table, and you can also use Excel. I'll show you how to use the Excel tool. Sigma is basically standard deviation of population. This is known. Okay, this is sample size. And this entire thing is called margin of error. Okay, so this is the same as the D, plus and minus D. We used it in the previous calculus. You're going to see that. Here what we have, D% confidence interval. And for mu, this is the formula. And that's sigma square root of n and z star. The definitions are here. Just make sure that you have SRS. If you don't have SRS, we're going to have problems. So Z star is the same thing as, no. Z star called critical value. The whole thing, Z star times sigma divided by square root of n, that's called margin of error. Z star. Z star, this is called critical value. This entire thing, it's called margin of error. Okay. And the X bar is estimating basically the mu. So we went through this Z star critical value in the standard normal distribution. Yeah, we talked about it. C is the confidence level for the distribution percentage, 95%, 68%, whatever the value is contained underneath the curve. And the interval is between minus Z star and plus Z star. You saw that, right? So when we calculated this one, so this was your Z star over here was basically this is the normal distribution, right? Normal distribution, normal distribution. But if you go for standard distribution, the case of standard distribution, this is 0, that is 1, this is 2, that's minus 1, that's minus 2. This is normal standard distribution. So here, so we're looking at, this is Z value, Z star. So when you say Z star 2, that means it's minus 2 and plus 2, and that means 95% here. Okay? All right. So that's the reason we put minus and plus there. So critical value, you can see it on page 701. Let me show you that. You have these tables. So this is C, table C. You can see that. On the top, you see confidence level C. This is what we have. 50%, 60%, 70%, 80%, 90, 95, 96, 98, skips 97, 99, 99.5, 99.8, 99.9. So you can see that when you look at this one, you're going to pick 95% confidence interval. Remember, it was 2, right? But if you do this, look at down here. Let me get my ruler. So if you go from 91, 95% all the way down here, see, this is 95% all the way down. What do you see? This is the Z star. What do you see? 1.96. See that? That's how you're going to look at it. And that's going to be your Z star. When you use a table in the midterm exam, that's how you're going to put your Z star value there. If it matches with these numbers. If it doesn't, then you have to go back to the A table, table A, and calculate from there. So this is much easier to look at it. And remember the one that we have, 68%, 95, 68, 95, and 99.7. 95 there was 2 instead of being 1.9. That was estimate. That was like approximate. It wasn't exactly, it's not actually exactly 2. When you deal with 68%, it's not exactly 2. Basically, it's, I mean, 95%. It's 1.96, not 2. Okay, let's see. So I'm going to draw this. If you go to that page and look at it, I'm going to draw this and show you again. This is the normal distribution. And here you have mu. This is you have mu plus sigma over square root of n. This is mu plus 2 sigma over square root of n. And you go to the mu plus 3 sigma over square root of n. On the left side would be mu minus 1 sigma over square root of n, mu minus 2 sigma over square root of n. So this is up to here, you're covering 99.7%. Again, if it happens in the middle, then you got to do some other calculations. But if it happens to have the numbers that you saw on the table C, then you're okay. You use that table. And if you convert this to normal standard distribution, then the middle part is going to be 0, and the one is going to be, it's going to be, you're going to have 1. That would be Z star. Now you're putting Z star here. It's going to be 2 Z star, and that's going to be 3. On this side, it's going to be minus 1, minus 2, and minus. So you're calculating your Z star from there. All right, let's do one example here. 2 of them, we have it. Find the critical value Z star for the indicated confidence level. Confidence level is 95%, right? So we can do it 2 ways. We know that if we just go with the 68, 95, and 99.7, this is going to be 2 sigmas. So it's going to be 2. Z star would be 2. But if we use a table, you saw that if I use a table, I'm going to put on up there again. This is, don't worry about degrees of freedom. This is the T distribution. Don't worry about these numbers. We'll talk about those numbers later when we get to the T distribution. So we have, look at here, confidence level C, it's 95%. Go all the way down and look at the Z star, that shows 1.96. So therefore, if we use that, Z star is 1.9, 1.96, and if you plot this, it's going to be like, that's going to contain 95%. What does it say under 95? Under 95? What 95? This 95? What does it say under 95? I don't know what that question is. Under 95. Where's 95? Talk about 95%. Okay, so this is part A. Part B is 99%. So 99%, so we're going to look at here again. So confidence level is 99%. Confidence level is 99%. So Z star would be 99%. 99% is here. If you go down, all the way down, it would be 2.576. This blue row, that's for Z star, would be 2.576. So that would be 2.576. And if you look at it in terms of the curve, under the curve, so 90, what was it, 99%. So that would be 2.576. This would be minus 2.576. That is 0. And this entire thing contains with 99%. Okay, so now if you want to, well, Excel will show you Excel later. Let me just make sure that we go through this. Make sure that you got the concept. Because 97% is not on the table. If it's not on the table, then we are going to go look at something else. See that? This is 96 and 95. It jumps, 97. So it has to be between these two values, somewhere there, right? But we have to calculate what that value is. We can use table A. And since you asked the question, we might as well do it, right? Let's see. Okay. If I want to do that, so I have to look at here. This is table A. So you said 97. 97%. Look at 97. This is 97, 19, 97. And then we'll go back here. This is most likely the candidate for 97%. If you look at that and see that the 97%. Oh, the problem with this is more than that. I got to explain more things here. Because when you say 97 here, you got to calculate the area and find the area and then calculate this 90. Let me do this later because it's not just that 97. It's not that easy. It has to. You have to add. I'll do it in the next slide. It's not that easy. Okay. Let me go through this. I'll show it to you next time in the next one. Find the confidence interval for the mean of normal distribution with sigma is 4 and a sample means of 6.8 obtained from SRS have 65 observations at the indicated confidence level C, right? So we have sigma is 4, we have X bar is 6.8, and we have the size of the sample is 65. So if you want to find the confidence interval, so it says 95%. So 95%, we got that Z star is from here. I'm going to say confidence level is 95%, and that represented by Z star to be 1.96. You saw that from the table we did this, or you can look at the table, you can get this 1.96. Now, confidence interval is equal to, we have X bar with the lower, I'm going to write Z star sigma over square root of n, comma, X bar plus Z star sigma over square root of n. So that is the estimate we are doing for population mean, and this is the error. That is the Z star is the critical value, sigma is the population standard deviation, n is the sample size. So we can calculate this. CI is equal to X bar is 6.8 minus Z star, we said we calculated, it's 1.96. Sigma is 4. Square root of n, it's square root of 65, comma, and then we have to add instead of subtract that. 6.8 plus 1.96 times 4 divided by square root of 60. Okay, so if we do the calculation, you have the confidence interval is equal to, you have 5.828, and on this side you have 7.772. So that's it. That's as simple as it gets. So when you're going with the population mean, you had basically what it says. You had SRS of 65 observations. You calculated the mean of this observation, 65, you came up with 6.8. Knowing that the population sigma is 4, and you wanted to know what would be the population mean with the 95% confidence interval. So if we do this 65 observations 100 times, this is one time we did, and we calculate the confidence interval out of 100 times, 95 times, we definitely know that it's going to happen between these two numbers. Between these two numbers for every sample. It's not going to be exactly the same numbers. It's going to be different numbers. But all it says, so if you're calculating mean of one sample with the confidence interval of 95%, so you know that your mean is going to be between those two values 95% of the time. You got to differentiate this with it's not 95% of the population mean is going to be there. It is if you do the sampling 100 times out of 100 times, 95 times out of 100, you find the population mean to be within that interval. Doesn't mean that 95% of the population mean is going to be there. There's a difference. We can do it for 99%. For 99%, we know that confidence level is 99%, or you call it C. From here, Z star becomes, we got it from up here, it's 2.576. So CI, basically, it's going to be equal to, so you have 6.8 minus, then you have 2.56 times 4 divided by square root of 65, comma, so you have 6.8 plus 2.56 times 4 divided by square root of 65. You do that, you do the calculation here. CI becomes, based on my calculation, I have 5.522, 8.078. Now, notice that when you compare, when you increase the confidence interval, here was 95%, here is 99%. You can see the whole thing gets wider. The interval gets wider. Here it's between 5.8 to 7.7. Here it becomes between 5.5 to 8.0 or 8.1. So this is wider. And the reason for that, you can see from the calculation here. Excuse me. Okay. Here you see from this formula, if you increase Z, this is going to increase. If you increase sigma, that's going to increase. Only time this part has become smaller when you increase the sample size, because that's in the denominator. So anytime when you increase confidence level and sigma is increased, your confidence interval is going to get wider. And anytime when you increase sample size, the sample size gets bigger. So therefore, this confidence level, the interval is going to become smaller. Let's do number here. I think we have it here. So what I'm going to write, this one I'm going to formulate in a way that you can see it easily. So confidence level, let's call it C plus, C star. If this goes up, conclusion is CI is going to become wider. If sigma increases, then CI again is wider. If N increases, sample size, CI is narrower. And based on this simple formula, when you look at this, because X bar is the same for both of them, just see that. This is C percent, that means Z star is going high. This is going to become bigger. Sigma gets larger, this is going to become bigger. And if N gets larger, this becomes smaller. When I say C percent gets larger, or confidence interval gets larger, I'm assuming the rest of them is not changing. If I just increase the confidence level, the things are going to change. Like in this case, I'm assuming confidence level is not changing. If I only change sigma, the entire confidence interval is going to change. All right. Okay, let's do one more example here. I wanted to go back to what Olivia, I think, asked the question. I want to do, trying to find the blank paper, do the example that, okay, what I want to do, I want to do something that you can see, you can use Excel, and also you can use tables and calculator. What I want to do, I want to first do something familiar. If you're okay with that, then I'll move on. If you don't, then I'll do that 97%. Okay? So here, what we have, remember, we had this one. This is for Z star, right? Z star, we said if you go with the table, you can find this is 1.96, table C. This is table C. This is that 98, 68, 95, 99.7%. You know, we had that rule. So it gives you 95% would be here. That would be 2 sigmas. That's 2 in this case. And also, you can use Excel to do this, and you can use table A. So for table A, if I want to say 95%, so I know that 95% is going to be here, right? So I'm looking at Z star here, and this would be minus Z star. Right? We are looking at 95% of the table. So what we want to calculate here, so I want to calculate this Z star. I know this is 95%. And I know that anytime when I use the table, Z table, I have to say to the left of Z star, but I don't have this area. So I need to find this area, add it to 95%, and then I say I can find Z star. That was the reason I said it's a little bit more complicated. So that's easy to do that. So this is 95%. So the rest of these two, it's going to be 5%, and each is going to be 2.5%. So now to the left of Z star would be what? 97.5%, right? I hope you guys are following me, what I'm doing. Yes? Good, good. So now this becomes, now I'm calculating Z star, so this is 97.5% or 0.975. That's the area we're calculating. So I can look on the table, table A, 90.97. Okay, okay. Table A is this one. So we're looking at 0.975, 0.9, 0.9, 0.975. Okay, you can look at it here. 0.975. Do you see it? Point 0.975. 0.97. You see that? 0.975. So that would be 1.9. If you look at it up there, I put this value there, it becomes 1.96, right? Use the table. It's exactly the same as C table, and this is the A table, table A and table C. So therefore, this corresponds to Z star is 1.96. Also, if you want to calculate this, you got to use in Excel. In Excel, you do the same thing. You're going to say equal. This is in Excel. So you have to say Z star is equal to, that would be normal dot, uh, you need to use standard dot inverse. And you have to put this number here, 0.975. And if you do that, you get more accurate answer. It's going to be 1.95996. So this is an Excel. You're going to see that you're either Z star is given or you're going to calculate Z star. It's not as simple as putting 95% here. You got to understand this is the Z star here. So you need to put the area to the left of Z star, and you have to add this tail, the area due to this tail, the original 95% in order to get the right answer. Okay? So if you want to do it for 93%, 97%, you do the same thing. So you have to calculate this. So 97%, so I'm going to put it 97% here. So you have 3%, so that would be 1.5% here and 1.5% here. This is the Z star. Sorry. This is that, I think it was Olivia or someone asked that question, 97%. So this would be 97%. So you're looking at this Z star here. So the difference, 1 minus 97, 97%, you have 3% equally divided. 1.5% goes to here, the other 1.5% goes to this tail. So you're looking at the area to the left of this. That area is 98, 98.5% or 0.985. So if you want to use Excel for this, for 97%, then you say Z star Excel. Then you say Z star is equal to norm dot S standard dot inv. Inv is the inverse. You're going the opposite direction. And you put 0.985. You get the critical value. If you use, and you can use table C, because in table C you saw that you don't have the exact value. Let me just show you. In table C, 97 is here, right? 97%. If I project that 97 and come all the way down here, it's going to be between these two numbers. It's going to be between 2054, 2.326. Let's use the table A to see that number is going to lie between those two numbers. So we got this 0.985. So 0.985. Where are we? 0.9, is it 0.985? 0.986, 0.9, 0.9, 0.985. There we are. So if you look at this number, 2.1 other, that's 2.9. So we're looking at that number. it would be 2.17, right? For 97%, it would be, if you look at this one, this would be 2.9, 2.17, 2.17. So if you do this, this is going to be 2.17. And what was the C table? C table, table C. So you can see 2.17 lies exactly between these two numbers. This belongs to 97%. Okay? That is, we calculated 2.17. All right. I hope that it's okay that you asked that question. And when I said it's a little bit complicated, that's what I meant. You have to calculate the area, total area to the left of Z star. Okay. So let's go back to what we did here. We are done with this part, right? I was working on this. Now, will we have to do this for our Excel homework? There's a possibility that, yeah, in Excel you're going to do this. Yeah. If the question is find the critical value for 97%, then you got to calculate it that way to find the critical value. You can't put just 0.97. You got to put 0.985, 0.985, yeah. But you have to understand why you're putting that. Don't memorize it. Just I show you the I showed the picture. 97%. When you calculate it, this is the 97%. But when you calculate the Z star would be the area, the total area to the left of this. That means you have to add this 1.5% to that 97%. All right, let's go. Well, let's do another example. 99% confidence interval does not mean that, here it's good, just pay attention to this, does not mean 99% of the population lies in the interval. It doesn't mean that. All it means that if you do the testing, sampling 100 times, out of 100 times, 99 times, you're going to see that the mu is going to be within that interval. It means that if we found confidence interval for many samples, 99% of them would contain in the actual mu. Okay? You might have a question with regards to that. All right, let's go to example 4. Example 4 is the following are data for thickness in centimeters of tree bark obtained from an SRS. Let's assume that sigma is 1.3 centimeters for the population. So sigma is 1.3 centimeters. So if we want to do this example, so how many do we have here? 1, 2, 3, 4, 5, 6, 7, 3. That's 21, right? So the sample size is 21. Sigma is that. Now we got to find X bar. We don't have X bar. This is my sample. I got to find the X bar. And if I wanted the X bar, what do I do? Okay, here, what do we do? Do we need X bar? Yeah, for here we're going to need X bar. But at this time, I don't. Right? It says make a histogram of the data. Is there evidence against the conjecture that the data comes from a normal distribution? We got to find the data for this. So in order to find data, remember histogram. If I want to draw the histogram, plot the histogram, how do I do it? Histogram is, so I have, what is the smallest value? Smallest value is 1.3, 0.3, 0.3. So I will go from 0 to 1. So it's going to be 0 to 1. Then it's going to be 1 to 2, 2 to the 3. What's the highest? 4. Highest is 4, right? 2 to 3, 3 to the 4, 4 to 5. Remember this? When you put a square bracket, that means it includes this 0. When you put a parentheses, that means it goes up to 1, not including 1. Okay? So the same thing goes here. Now, this one includes 1, but this one doesn't include 2 because this is a parentheses, and the same thing goes with all this numbers. So let's count the number here because we want to. So this is going to be 0, 1, 2, 3, 4, and 5. We're going to plot this. So what do we have? Between 0 and 1, let's see. Between 0 and 1, this is 1, 1, 1, 1, 1, 2, 2, 2, 2, 2, 2, 2, 2, 2. I have only 2 data points. Between 1 and 2, so 1 point something all the way to 2. 1 point something, that's 1. 1, 1, 1, 2, 2, 3, right? 3. We have more? Did I miss something? Between 1 and 2, oh, I have another one here. 4. Oh, I have another one here. 5. Gosh, I'm tired. So I have 5 of them, right? 1, 2, 3, 4, 5. This goes to 5. Between 2 and 3, I have to, let's see how many I have. I have to be careful now. 1, 2, 3, 2. 2 is included. 3, 4, 5, 6, 7. So I have 7 of these. Between 3 and 4, 1, 2, 3, 4, 5, 6. I have 6 of those. Between 4 and 5, 1, I have 1. So if I want to plot this, so this is going to be, maybe I should make it smaller. That would be 1, that would be 2, 3, 4, 5, 6, 7. So between 0 and 1, I have 2, so that would be here. That would be that column, between 0 and 1. Between 1 and 2, I have 5. 5 would be here. So I'm going to write 2 here, 5 here. Between 2 and 3, you have 7. 7 would be all the way up there. That would be 7. Between 3 and 4, that is 6. 6 would be here. Between 4 and 5, that would be 1. 1 would be here. All right. When you look at this, this is almost, you can see that it's kind of symmetric, if you can see that. You can go like this. Yeah, I can call this one normal. So basically there's nothing against this conjecture. Basically this is normal. Call this one, at least distribution appears to be normal. Normal and symmetric. And the mean is going to be somewhere here. So it's going to be between 2 and 3. Whatever the number is, that's going to be the mean. That's going to be x bar. We can verify that x bar by calculating the mean for this number, the numbers we have here. And we need to know that. Actually, we need to calculate that x bar. So we are okay here. All right, I'm going to make this one up a little bit. All right. 96% confidence interval. So that's 96%. That corresponds to, do we have 96% on the table C? Or no? We do have 96%. This is 96%. If you drop down all the way there, it's 2.054. This corresponds, Z star is equal to 2.054. Okay, then if you remember, if you want to write the confidence interval, then you need to have X bar. So what is X bar? X bar would be, you got to add all these numbers, 3.0 plus 3.2, all the way, you have 21 of them, 1.6 divided by, we said there are 21 of them, divide by 21, and I calculated this somewhere here, just let me see if I can find it. It's 2.3. Notice that this X bar is 2.3. I told you that it's going to be between, you saying, see, from the figure, it's going to be between 2 and 3. So based on a calculation, is 2.3. Okay. Now we have to calculate the confidence interval, right? We have the confidence interval. We have to, for the mean thickness, what is it? Construct a 95% confidence interval. So CI is equal to, you have X bar minus Z star times sigma over square root of n, comma, X bar plus Z star sigma over square root of n. I have all the values here. Ci would be equal to, X bar is 2.3 minus Z star, we said, is 2.054. Sigma is, I got to write sigma is 1.3. And base what we have here, n is 21. Okay. Sigma is 1.3 square root of n, that is 21, comma, X bar plus 2.054 times 1.3 divided by square root of 21. And if you simplify this, CI is equal to, I have it somewhere, it's 1.72, comma, 2.88. That would be the average. If you have a sample of 3021 and do the sampling with the confidence interval of 96%, definitely 96 times you're going to see that if you do the measurements, your mu is going to be between those two values of measurements you do. Okay? Oh, well, okay, I guess the time is, okay, we'll do the rest of this on Monday. And hopefully Monday I'll do chapter 16 and 17, maybe next week. So if you don't have any questions, I'm gonna turn it off and go have fun. No questions? All right, folks. You have a good afternoon. And I'll see you on Monday. Good weekend. Bye-bye.